used to literally get lost in broadest. How do you do that? I don't know.
So let's resolve this problem. What is the final temperature after putting 100 grams of negative 10 degrees Celsius ice into 500 grams of 20 degrees Celsius water? I only made one mistake yesterday. It's just that I didn't expect the final answer. So, CP for ice, it will use 2.04 joules per gram degree Celsius. The heat of fusion of water is 334 joules per gram. And the CP of water is 4.184 joules per gram degree Celsius. So we can draw a little picture. So remember conservation of energy. As long as no external forces are applied, if you completely isolate a system, the energy is conserved. The amount of energy you put into a system is going to be the same. If you don't put any energy into a system, then the total energy flows are going to be constant. So we're starting out with a negative 10 degrees Celsius ice. That's 100 grams. It's going to melt, or it's going to heat up first to the melting point, 0 degrees Celsius. And then it's going to melt. And I predict that when I put ice into water, the water doesn't freeze. It is possible. For example, if you put ice that's at negative 200 degrees Fahrenheit, so if you go to Antarctica and you put in some ice that's super, super cold into some water, then the water will freeze because the ice is all the energy required to heat up the ice is will make it so the final temperature is below 0. So in this case, we're going to have to guess what happens. The final temperature is going to be, basically you have to guess. Mathematically, you can look it up. If you get a value that is negative, you have to rework it. But you can use your intuition and know that most of the time when you put ice into water, the ice is warm enough that it will not freeze the whole water. So I'm going to predict my final temperature is going to be somewhere above 0. And the water, from the water side, is going to be at 20 degrees Celsius, room temperature, 68 degrees Fahrenheit. And that's our 500 grams of water. Even though the final result looks something like this, we have a container full of water with some ice cubes in it. And we end up with the ice cube melting. And we end up with just water at the end. However, we can separate our system so it looks more like this. We have a glass of water, and we're placing an ice cube next to it. And we'll put this in a container by itself too. So that the heat flow, the heat going from here is going to flow into this. And remember that we're going to isolate this from the rest of the universe. no heat is going to be able to leave the system, so we're going to put this in a bubble. No heat is going to go into the system, warming it up, and no heat is going to leave. So this means that the total net flow of energy is going to be 0. So the heat gained by the ice plus the heat lost by the water has to be 0. Because the total net flow inside this bubble is a 0 joule sum. There is no heat going into it, no heat leaving. Perfectly black box where nothing's going in, nothing's going out, so I expect a net change in energy to be 0. And this leads us, solving for this equation, that the heat gained by the ice will be equal to the negative heat lost by the water. This is where this equation comes in from yesterday. It comes from the fact that there is a net flow of 0 energy into and out of our system. So we're going to break this up into steps. We're going to have from negative 10 degrees Celsius ice to 0 degrees Celsius ice. This is a change in temperature. There is no phase changes in between. So we're going to use the change in temperature heat equation. Q, the amount of heat changed, is going to be equal to mass, the ice, times the CP of the ice, and it's going to be multiplied by the final temperature of the ice minus the initial temperature of the ice, our delta T. So this is our final temperature. This is our initial temperature. So solving this out, so we have mass ice, it's 100 grams. Mass of the water is 500 grams. Initial temperature of ice is negative 10 degrees Celsius. And the final temperature of the ice is going to be 0 degrees Celsius water. And let me make sure to put subscripts, not to confuse it with STF. So we get 100 grams times 2.04 joules per gram degrees Celsius. And we're going to get 0 degrees Celsius minus a negative 10 degrees Celsius. The minus a negative makes it positive. So 100 times 2.04 times 10. And I get 2,040 joules. Yesterday I did it wrong and got like 20,000 or 10,000.
Right. 10,000.
Yeah. I don't know what I did wrong yesterday in my calculator, but I'm separating it out. So this is this portion. So this is this area. Now we need to deal with melting. So this is that. Now we need to handle the case where it melts. So melting. This is where we're going from 0 degrees Celsius ice to 0 degrees Celsius water. And because I'm doing this scenario, I'm going to call the mass still ice, even though it's going to turn into water, just to separate that it's the original mass of the ice. So the original mass of the ice, so we use this equation, mass of the ice times the heat of fusion. So that would be 100 grams times heat of fusion for water is 334 joules per gram. Being very careful not to make any mistakes. That's 33,400 joules. Now we're going to reach our final temperature. So we're going to go from, and this is only solving the heat gain section. This is only solving when looking at the ice cube. What is the ice cube doing? So the ice cube is going to go from negative 10 degrees Celsius ice to 0 degrees ice. Then it's going to melt. It's going to go from 0 degrees Celsius ice to 0 degrees Celsius water. And finally, it's going to go from 0 degrees Celsius water to some final temperature. And I should be using capital letters for T. Lowercase letters is time. Capital letters is temperature. And it would be water too, so there's no phase change. So it would be Q equals the mass of the original ice times, but now the phase is water, so we'll use Cp of water. And we do the Tf minus Ti for this portion, which Ti is 0. So this cancels out because it's 0. So that would be 100 grams, our starting mass. And we'd use 4.184 joules per gram degree Celsius. And it'd be times Tf. So this would be 418.4 grams cancel out, giving us joules per degree Celsius times Tf. So these three things represent or heat gained by the ice. So heat gained by ice is equal to 240 joules plus 33,400 joules plus 418.4 joules per degree Celsius times Tf. And we can simplify that down to 35,440 plus this would be joules plus 418.4 joules per degree Celsius times Tf. So this is our equation by how much energy the ice received to heat up before it reached equilibrium. Now let's look at the heat loss section. The water is going to start out with 20 degrees Celsius water. And it's going to go to some final temperature, water. So this is going to be a change in temperature, water to water. So we do the mass of our original water times the Cp of water. And then we're going to do final minus initial. So 500 grams times the Cp of water is 4.184 joules per gram degree Celsius. Tf minus 20 degrees. So 500 times 4.184 is 2092. Grams cancel out, so joules per degree Celsius times Tf minus 20 degrees Celsius. And then we're going to FOIL this times that. So 2092 joules per degree Celsius times Tf. And then this times this. So minus 41840. The degrees Celsius and the degrees Celsius cancel out, so we get joules. So our heat lost, and And let me put a box around this. So our heat lost by water equals 2092 joules per degree Celsius times TF minus 41840 joules. Because no energy has left the system, we know that the sum of energies have to equal 0. Or, in other words, heat gained has to equal negative heat lost. So we have our equation for heat gained. It's 35,440 joules plus 418.4 joules per degree Celsius times TF. And this has to equal negative, big parentheses, 2092 joules per degree Celsius times TF minus 41840 joules. So simplification, we're going to distribute the negative in. So this becomes negative 2092. I'm going to start reading off units. TF, negative and a negative becomes a positive, 41840. And on this side we have 35,440 plus 418.4 TF. We need to combine like terms. So moving this over to this side. So we're going to add negative. We're going to add 2092 to both sides. Has a TF next to it. So we get on this side TF. And then we're going to move this over to this side by subtracting it. And we're equal to 6,400. And now we divide by 2,510.4. And we get a final temperature of 2.5494 degrees Celsius. And that's our answer. Our initial guess was good. We guessed that the number, our final number, would be between 0 and 20. That's something you have to double check. I don't give any problems where you have to redo it like this. But if we got a negative value, we have to completely redo the problem. Because our math assumed that the ice is going to melt, and it changes the equations in order that we do it. There is an equilibrium point, though, in real life, where if you put an ice cube in a drink, statistically, in thermodynamics, it's more likely that the water will not freeze and you have an equilibrium where the ice just never melts. Where all the water reaches 0 degrees, and that's a very complicated situation to work out, but I don't do it in this class. So does that make sense? I personally like solving these problems completely using algebra and one equation. But I admit, it is very, very easy to make a mistake. The reason why I like doing it is because I can write a general formula. So let's suppose we start at some temperature 1 for the with a mass here. We go up to some melting point. And then we're going to go up to some final temperature, TF. And let's say the water begins at some temperature, T3. And it's going to go down to some final temperature here. And instead of calling it ice, I'm going to call this M1 and this M2. And I'm going to assume during this portion it is solid. It melts. And during this section right up here, it's liquid. This means our equation, we're going to go from T1 liquid to T2 liquid. And let me draw arrows. Then we're going to go to T2, and this should be solid. So start with T1 solid to T2 solid to T2 liquid up to TF, which should also be liquid. And on the other side, we have T3 liquid going here. So this side is going to be our mass 1. And this side is going to be our mass 2. Each arrow represents an equation. And at this side, right here, this is going to be our heat gain section. And it's going to equal negative heat lost, because the arrow's in the opposite direction. So we can come up with a general formula and solve for TF. So we get mass 1 times CP liquid, or solid, times T2 minus T1, plus mass 1 for the melting, H of F, plus M1 CP liquid. And we're going from, so this arrow, so this is this arrow, this is that arrow, and then we're going to go from TF minus T2, so this equation is this arrow. It's going to equal negative mass 2 times CP of liquid, and then we're going to go from a final to initial, so TF minus T3, because the arrow's in the opposite direction. Note that if you switch TF and T3 around and backwards, the negative disappears. And doing some algebra. So I want to put all the TFs on the same side. So I want to move this to the right side. And this to the left side. And so what we get is mass 1. And let me come over here and make this even more generic. I'm going to have on the left side, since the left side is going to be our first object, I'm going to put 1s by the CPs. I'm going to put 1 by the HF. I'm going to put a 2 here. This does the situation where if we're putting not water, not frozen water, like something else. So this would be this equation, CP1, this is liquid. Liquid times TF minus T2. When I'm moving this over, it becomes a plus. So mass 2, CP2 liquid. And then it's TF minus T3. And moving this section over, it ends up with minus M1 CP1 solid times T2 minus T1 and minus M1 HF1. FOIL these out. So mass M1 CP1 liquid times TF minus M1 CP1 liquid times T2 plus, now I'm going to FOIL this out, so M2 CP2 liquid times TF minus M2 CP2 liquid times T3. We don't have to FOIL the right side out because we're only trying to solve for TF. And then we do again. We move everything that doesn't have TF to the other side, which would be these terms. So we end up with M1 CP1L times TF plus M2 CP2L times TF. And this would equal, moving these to the right side, would be M1 CP1L T2 plus M2 CP2 LT3 minus, now on the right side, M1 CP1 solid T2 minus T1 minus M1 HF1. This right here can be, you can factor out the TF. This becomes M1 CP1L plus M2 CP2L times TF. And then we can simply divide and we get the final equation. So the final generic equation for a situation like this is thus original mass of sample 1 times the CP1L times T2 plus M2 CP2L T3 minus M1 CP1 solid times T2 minus T1 minus M1 HF1 divided by mass 1 CP1 liquid plus M2 CP2 liquid. And this is the generic equation for if you put a solid in a liquid and that solid melts, this is the final temperature. You can clean this up if we assume object 1 and object 2 are the same substance. We can get rid of the CP, the 1s and the 2s on the CP. So liquid. We can factor these out. Let's see if there's any factoring we could do. It's probably best not to even factor it out. This is good enough. You could just remove the 1s and the 2s on the CP. This is how I would solve it. I would check and make sure this makes sense. I would try an example. I would plug it in. Then I'd set my calculator up to where I can program in mass, CP, and stuff like that, and have it automatically spit it out. The reason why I present this is put a star by this in your notes, as tomorrow we're going to go do this. we're going to put ice into some really hot water. And I want you, before the ice melts, to tell me what the final temperature is. And then we're going to see if you're right. Now, what temperature is ice at?
I don't even know. I just know water freezes at 32 degrees.
We don't use Fahrenheit. 0 degrees Celsius. So, do you think that whenever I go to the lunchroom and ask for ice and bring it back to the lab, what temperature do you think the ice is going to be at? 0. It might start out at -10 or -5, but I guarantee you on the walk over, it's going to very soon start melting. By the time I actually start putting the ice in, it's going to warm up to 0. So, if the ice has already reached the melting point, T2, so T2 was the melting point, we can simplify this down to, so what are we doing? We are basically removing this M1 CP1L TF, this one, M1 CP1S. So we're basically removing this. So it becomes M1 CP liquid T2 plus M2 CP L T3 minus M1 HF divided by M1 CP liquid plus M2 CP liquid. What does every single term in this equation have except for one?
The liquid?
Yeah, CPL. So if I divide this by 1 over CPL and 1 over CPL, this is 1, right? Anything divided by itself is 1, so if I multiply it by this can simplify down to M1 T2 plus M2 CP, not CP. So this would equal M1 T2 plus M2 T3 minus M1 HF over CPL divided by M1 plus M2 is the final temperature. This assumes objects are same chemical and the solid object is at melting point T2, which cleans up the very messy equation significantly. So let's use this and see what would happen. Let's do a real example using this generic equation. So using this, which I highly recommend other than a lab setting where I'm doing this, we don't. So if we have 0 degrees Celsius ice and we have 50 grams into 80 degrees Celsius 200 gram water, what would be the final temperature? So our T2 is 0 degrees Celsius, or M1 is 50 grams. And here we have our T3 is 80 degrees Celsius, and our M2 is 200 grams. This is basically what we'll do. We might do like 25 grams of ice. Then our equation, final temperature, would be mass 1 is 50 grams, or T2 temperature is 0. So that cancels out. Plus mass 2 is 200 grams. And T3 is 80 degrees Celsius minus 50 grams times heat of fusion, which is 334, divided by the CP of the liquid, 4.184, all divided by the sum of the masses, 50 plus 200. And I get a final temperature of 48.0344 degrees Celsius. Make sense? All right. So let's do some more problems. Oh, what happened on the test? The ones that have directions on it is where you messed up on. You got like all those wrong. So let me look up some values for gallium. Do you know what gallium is? Gallium is a metal that is solid at room temperature. So it is solid at 68 degrees Fahrenheit, but is liquid. Let me look up melting point of gallium. It is liquid at 85.58 degrees Fahrenheit. So it melts somewhere between room temperature and your internal body temperature. Which means if you hold it in your hand, it will melt in your hand. So the only true metal that is liquid at room temperature is mercury. But gallium's also sometimes included into that. Just because it melts at basically temperatures we're used to. Yeah. I hate whenever it loses. So I need, so the melting point of gallium is 29.76 degrees Celsius. Yeah, I don't know if I can get... Where's the value? I don't want the molar heat. I want the specific heat. I think both the specific heat for solid is approximately the same as the specific heat when it's a liquid, which is approximately 0.37 joules per gram degree Celsius. You'll notice it's very different than water. Water has very different values for when it's a solid versus a liquid. And that seems about right. The heat of fusion of it is 80.1 joules per gram. So how much heat is needed to warm gallium from